Hello, Year 11, welcome back. We're going to look now at Wharf Crystallisation, which is the last kind of couple of pages of your booklet. We're on to page 17 here now. Now, we have kind of looked at Wharf Crystallisation before, but we didn't look in any kind of great detail. So, the key things about Wharf Crystallisation is first definition. Water of crystallization is water that is chemically bonded into the crystal structure. What that essentially looks like is this, or you might recognise it. A common substance that has Wharf crystallization would be copper sulfate, CuSO4. You can swap and drop that yourself. If it's got Wharf crystallization, you normally see a dot after it and then some H2Os. Now the number for the H2O will depend on the compound. All that basically means is it's still copper sulfate, but however it's solidified into a crystal, it's got some water trapped in it. So it is just individual water molecules, but they are chemically bonded to that. So we can't just say it's different. It is actually one thing. Key thing to spot is just that dot there to show it's actually bonded. Little definition there. If it has got Wharf crystallization, we refer to it as hydrated. So hydrated means the crystal contains Wharf crystallization. If it's anhydrous, it means it does not contain Wharf crystallization. Because one key important thing that we're going to need for calculations is to realise this. If I heat up something that has got Wharf crystallization, in the same way that if I heat anything which got water in it, the water is going to boil off, this will lose its Wharf crystallization. So the heat will release this 5H2O, and what you'll end up with is copper sulfate by itself, and then H2O's water's going off like as steam out into the air. If I've got rid of the Wharf crystallization, it's now anhydrous copper sulfate. So this is hydrated because it's got Wharf crystallization. This is anhydrous because it's lost Wharf crystallization. 3 points here we've already mentioned. The Wharf crystallization is separated from the rest of the formula by a dot, just like that. The number of molecules of crystallization is written after the dot. It's sometimes called the degree of hydration. So in other words, the degree of hydration of this particular copper sulfate is 5. It's got 5 waters attached to it. We then come to a calculation we actually looked at the start of the booklet, which is working out the percentage of Wharf crystallization in the compound. To quickly go over it again, we have done it before. Here's an example. Percentage of Wharf crystallization in tin chloride dot 2H2O. So basic format is I need to work out the mass of the whole thing, the mass of just the waters, and then divide that mass of the waters divided by the whole thing to get the percentage. Easier if you see it laid out. So SnCl2.2H2O need the mass of everything, including the waters. Tin's got a mass of 119. 2 chlorines, 35.5 times 2. And 2 waters now. Waters made up of 2 H's and an O, so 16 plus 2, 1 plus 1. Just going to call water 18. So 2 18s. Add that all together gets 224. I need the mass of the 2 waters, because there's 2 waters within the compound. That is just 2 times 18, the mass of 1 water, which is 36. Therefore, the percentage, according to this equation, or just kind of using your common sense, is the mass of the waters, 36, divided by the mass of the whole thing, which is 224, times by 100. That comes out to a whole number as, well, nearest whole number is 16%. So a calculation we've done before. A few kind of exercise questions here, just about how you write Wharf crystallization and how you actually calculate percentages. Well, pause the video here now, have a quick go with those in terms of how you write these formula and then doing these calculations. For the first part, you just have to work out the relative mass of all these things, but then you have to work out the percentage of Wharf crystallization afterwards. So I'll run through those now. 54, if it's got 7 Wharf crystallization magnesium sulfate, you'll have to swap and drop magnesium sulfate. So Mg is 2 plus, SO4 2 minus for sulfate, so it becomes MgSO4.7H2O. Sodium carbonate, sodium is group 1 plus, carbonate is CO3 minus in your periodic table. Swap and drop becomes Na2CO3 dot 10 moles 10H2O. Your mass for this bit is just a bit of calculator work with your periodic table. 177, 250, 244, 147, and 236. If you then do the calculation to divide the masses of the waters out of that whole thing, your percentages of Wharf crystallization becomes this: 41%, 58%, 15%, 24%, 31%. So I did those very quickly. There could be a wee mistake in here, so don't panic if you're getting different to me, but just let me know. But hopefully those are what you got as well. So a little bit more to do. Similar to what we looked at with empirical formulas, you could do a wee calculation based on an experiment. So this is how you'd experimentally work out how much wharf crystallization you've got within some crystals. The example we look at is copper sulfate, as I showed you at the start. It's got 5 waters attached to it. If you heat it up, it's going to lose its waters. In this particular scenario, I don't necessarily know how many waters there are, and I want to calculate the number of waters within that formula. The general method is similar to what I did with the empirical formula, but I need to realise it's going to get lighter. This is a compound. I've lost part of the compound as steam, therefore the mass is going to go down. So with before we had the mass increasing, with this one the mass is decreasing because it's getting lighter. Method is very similar though. I'll take an evaporating dish, I will weigh it, I'll then weigh it with my solid. I'm going to heat it. Now you notice I'm not going to put a lid on this because I want the steam to escape. A lid would trap everything. Once I've heated it for a bit, I'm going to cool it down and weigh it. I'll then need to heat it up again, and I'll know once I've heated enough because the mass has not changed, it'll be heated to constant mass. So I'll say that again, I need to heat it, cool it and weigh it until the mass stays the same. Then I know all the water's gone, it's not getting any lighter. A few experimental points that could come up maybe in a 6-mark question. If I really roast it really hot, it might decompose. I need to kind of gently, so I need to kind of like heat it for a bit, then take the Bunsen out and heat a bit more. I might get a few observations, so I might get a change in colour. I might change the powder, so I might get more powdery rather than crystals. I might see steam be given off because steam is released, H2O, and I might get like some water kind of condensing at the side here, so I might get droplets at the top of my evaporating dish or on my boiling tube. Some substances we'll actually learn about in the next topic, chemical analysis, actually do change colour when they lose water. Copper sulfate is one of those. Blue copper sulfate will actually turn white when it loses all its water. Safety point, I'm heating this up and cooling it down. I need to make sure it's completely cooled down before I touch it. It's simple enough. And the solid may spit out, so therefore I need to wear safety glasses. So after all that, let's look at a wee calculation to see how this actually plays out. Look at a simple one first, then a more complicated one in a second. So this is trying to work out what is the actual formula of a hydrated wharf crystallization compound. So this more condensed one here. Calculate the formula of hydrated lithium sulfate if 3.76 grams of hydrated lithium sulfate produces 3.23 grams of anhydrous lithium sulfate on heating. So it gives me the formula there. Let's see what we're working out here. What that is telling me is this. I've got lithium sulfate, and at the start it's got some more of crystallization. I don't know how much it's got, but I know it's got some. I'm going to show that, use a wee bit of algebra here. .xH2O. I want to find out what X is. If I heat it, I lose all that water, so it becomes Li2SO4, Li2SO4 after it's lost the water. If I look at the masses here, I've got 3.76 grams of hydrated lithium sulfate, 3.23 grams of anhydrous lithium sulfate. So that's matching that up. It's 3.76 grams of this and 3.23 grams of the anhydrous stuff. So now I need to get to the working out. It's not actually too dissimilar to what we did for empirical formula. I need the mole ratio from lithium sulfate to water. Here's how I go about doing that. So I'm going to write them side by side. First step is working out the masses of each. The mass of lithium sulfate within that compound must just be what I had left over once I got rid of the water, 3.23 grams. The mass of the water must be the amount I lost, because it's gone from 3.76 down to 3.23. It's got lighter by a certain amount when I lost the water. Therefore, the water that I lost must be those two numbers subtracted from each other. I'm just going to go to my working out here, which ends up being 1.44 grams. I've got masses. I now need moles. Like we did before, moles is mass divided by RFM. So it's going to be 3.23 recalculation to work out lithium sulfate, the mass of or RFM of lithium sulfate ends up being 110. I'm sure you can do that by now yourself. Water 1.44, the RFM water is 18. Getting those two numbers in my calculator, it's 0.02 moles of lithium sulfate and 0.08 moles of water. Like before, I just need the simplest whole number ratio. Hopefully you can see that that's a 1 to 4 ratio, 0.02, 0.8. If I'm not sure about that, I can just divide both by the smallest number. It becomes out 1 to 4. So putting that into like the correct formula, basically what I've solved there is that for every 1 lithium sulfate there are 4 water molecules. So X is basically 4. The formula of this unknown compound is lithium sulfate, Li2SO4 dot 4H2O, because I worked out that ratio from my calculation. Last type of calculation just on that would be this. So same kind of idea, except the values are a bit more buried within the question. So it's got a few steps here. I'm just going to ignore that and just do it kind of from scratch. So if we have a quick go at this here now then. So this is an experiment to find out the mass of warp crystallization in hydrated magnesium sulfate. Okay, so I'm trying to work out, if you look at my mystery formula, MgSO4 with some waters. If I heat it up, it's going to go down to MgSO4. The masses are a wee bit more tricky to work out. I've got the mass of the empty evaporating basin, 12.73 grams. I've got the mass once I add the hydrated magnesium sulfate, 13.96 grams, and then the mass after I heated the constant mass. So, like I did before, first thing that I need to work out is work out the mass of the hydrated one and the mass of the anhydrous one. That's the start point. The mass of the hydrated magnesium sulfate I can work out just by looking at how much heavier the evaporating basin got when I added the hydrated magnesium sulfate to it. It's going to be 13.96 minus 12.73. That comes out as being not... Oh, hold on. Yes, not as right. That comes out as being... If I do it here... 1.23 grams. The mass of the magnesium sulfate once I've lost all the water will be 13.33 grams minus the evaporating dish because it's now lost all its water. So it's now gone down to 0.6 grams. I also need to work out how much water has been lost here. It's only got lighter because it's gone from XH2O down to no waters. So the mass that's been lost is coming just from waters being lost. The mass loss is 1.23 minus 0.6, which is 0.63 grams has been lost. So, given my ratio again of magnesium sulfate to waters, I'm going to start with masses. Have to be careful here, the mass I use has to be the anhydrous one, the one that's lost all its water, so 0.6 grams. The mass of the water I've worked out already, it lost 0.63 grams when it was heated, so that's the amount of water that's been lost. Moles next, just like before. I need to work out my RFM of magnesium sulfate, which is just 24 plus 32 plus 16 times 4, which is 120. So 0.6 over 120. Mass, moles of water, 0.63 over the RFM water, which is 18. Do those quick wee sums here. 0.65 by 120 ends up being 0.005, or 5 by 10 to the minus 3. 0.63 divided by 18 ends up being 0.035. Now, some of you might see that already, but it's a need to get a whole number ratio. I can divide both by the smaller number, which is this one, to get that whole number ratio. If I do that, that becomes 1, and this becomes 7. 0.035 divided by 0.005 is 7. It's a 1 to 7 ratio of the amount of magnesium sulfates to how many waters were there in the first place. Giving that as the proper molecular formula will be MgSO4. I now know my X is 7 because there's 7 waters per water, or 7 waters per magnesium sulfate. That gives me that as my final empirical formula. Now, just like before, just to give you a chance to see actually see a question, I'm going to look for one here. So it's going to go through one with you now, if I can find it. So here's one. Let's look together at question 13. Okay, this again within your Bible at the back, all your past paper questions. So this actually is the same as what's in your notes, I think. Yeah, it is. So I'm not actually going to look at it. Let's look at a different one. Let's look at this one, question 15. This will be, there's no marker on it. Hydrated aluminium oxide gives you an N for H2O. May be used as an abrasive. Calculate the degree of hydration. So it's trying to confuse you there. That just means what is the war of crystallization? Like how hydrated is it? If 3.12 grams of hydrated aluminium oxide were heated at constant mass, 2.04 grams of anhydrous aluminium oxide remained. Find the value of N. Let's just have a go at the first, pause the video, and then we'll look at it together. So how did I approach this? Just like I did before, I'm going to look at the two numbers I've got here. So this is a bit of a simpler one than one with involving a table, but it's the only one we've got at the minute. I've got 3.12 grams of hydrated aluminium oxide. Once I heat it, get rid of the water, it goes down to 2.04 grams of it. So, putting that together, when it still got its water, I had 3.12 grams of it. When it lost all its water, when I heated it till it didn't get any lighter, it went down to 2.04 grams of it. Therefore, if I work out how much water has been lost, the H2 going off, it's going to be this number, take away this number, that's how much lighter it's got. That's going to give me 1.08 grams if I subtract those two numbers from each other. Getting to my ratio now, I need the ratio of aluminium oxide to water. The aluminium oxide, it's what's lost the water, so it's 2.04 grams. The mass of the water I've worked out is 1.08 grams. So now I've got my masses, I need my moles. We have moles equals mass over RFM. Adding up the mass of aluminium oxide is we have calculating, this ends up being 102, 2 aluminiums and 3 oxygens using these masses up here. Moles will therefore be 2.04 divided by 102. Waters will just be 1.08 divided by 18. That comes out as 0.02. This comes out as 0.06. So again, looking for the simplest whole number ratio of these two parts of the formula. It's a 1 to 3 ratio. Therefore, the formula is Al 203 dot 3H2O, but the actual question is just looking for the number for N. Therefore, the N in front of the formula must therefore be 3. Okay, hopefully that makes sense, because again, email me or put in the Google Classroom and comment on the wee post if there's anything that doesn't make sense within this video.